Yeah, hi, and welcome to a new series called Crate by Crate. And here we will just walk over some of the most common Rust crates. One crate per video, just a quick introduction so you know your way around a little bit and can just start exploring more and start coding. So this time we will start with ndarray. And ndarray is quite cool because it's an abstraction over multi-dimensional arrays. And it also is a bit faster than usual vectors. So when you have some operations on it, like multiplying multiple vectors with each other, and those operations usually are a bit quicker than doing it by hand with vectors. So let's get started. Just for you to follow, this is crates.io. Here we can look for ndarray. And here you will see the library. Yeah, you see it has a lot of downloads, so it's a very commonly used crate. And you will find some information, but the most valuable thing is the documentation. Go on there. And here I would suggest you to start reading with the ArrayBase. In the ArrayBase documentation, you will find all the information you need. So when you go down here, you will see again some recommendations in this documentation area. So ArrayBase and the S is for slicing arrays, and there's ndarray for NumPy users. Can be nice if you're coming from NumPy because they're relatively similar, so you can learn how to do things that you already know how to do in NumPy. But in general, the ArrayBase is the more valuable documentation. You will see all the different types and also slicing, arithmetic operations, and conversions. Conversions are super useful, so you know if you're stuck in one type from an operation, how you can convert into another type, also how to construct them from vectors or slices. Yeah, but let's get started. I just prepared some a little walkthrough to make it a bit easier to understand the types. Let's close this for now and get started with adding ndarray, cargo add ndarray. Then we already see there are some features. So the standard feature is enabled by default. If you remove this, you can even use ndarray on microcontrollers like the Daisy Seed or on any target really, but it still needs alloc. So you have to enable some sort of allocator. The rest is not that interesting for now. Just there's some performance stuff like BLAS or Rayon. And with the ZRD, you can save the arrays in a file if you want that. It added ndarray in version 16, so we have the newest here. And let's get just started with the test. And I'll show you how to create those arrays in the first place. A good way to start, if you never used ndarray, is just adding all commonly used types, and those are defined in the prelude crate. You see, this module contains the most used types, type aliases, traits, functions, and macros that you can't import easily as a group. So that's a good way to start. If you write the finished program, you can think of just importing the ones you actually need to not have any type confusion. But most of the times that's totally okay to import all of the ndarray types. All right. And first, because ndarray is using heavily type aliases that can be constructed out of a chain of types, I want to start with those base types so you learn what the differences are and how they actually look underneath. But those base types, in the end, you actually never have to use them directly. So you always use the aliases. But I think it's very good to understand the type system. That's why we will start with this ArrayBase. Yeah, this is the general container of elements. And let's say we want to have, we can create, I don't know, from from diag, from element, but let's just start with the zeros. And then we can add a shape. So a shape can be added with either this array or with the union. It looks like this. I like to use the union because it looks kind of nice here. And then we can use a shape, I don't know, 2 rows and 3 columns. So that's actually the function you need, but you will see it doesn't work like this. So when we try to save this in an array, we will get some errors here. It doesn't compile because it doesn't know the exact types that are used inside of it. And this is a bit difficult to find out at the beginning, but I'll show you how it works. We need S and D. You see S is raw data and D is the dimensionality. So how do we fill those out? We can use the turbofish operator here and specify those 2 types inside of those brackets. The first one we need is the S, the raw data one. So, for example, we want F32. It would be nice to just specify it like this, but it doesn't work like with a vector. We still need to wrap our actual type in the type of container we basically want to use around it. So, in the easiest case, we can just use owned representation. Wait, it's not popping up here. Owned representation. This is, you see, this is not in the prelude because it's something we usually don't have to use ourselves. But here I just use it to show you how actually everything works. So the owned representation, if we click on it, you see it's like a vector, but with non-unique ownership semantics. Don't use this type directly, use the type alias, yeah, like it's saying. There are also different types of representations. We go into this later, but for now, let's stick to the owned one. That just means it owns the memory. It's actually allocating memory as well. And then let's go to the second one we need. And we need the dimensionality. So do we want to have a 2-dimensional array or a 3-dimensional array? And this can't be specified just with a number. You see that doesn't work. It has to be specified with this unique type, that is this IX. And here you see there is IX0 to 6, and then the dyn for dynamic arrays. Dynamic sized arrays can be used. They're kind of nice when you really don't know how many dimensions you have. But in general, I would suggest always stick to the strictly typed ones because the performance is just better, and also you can encounter less errors in multiplications and so on. Maybe let's start with the IX2. 2-dimensional arrays are the easiest to grasp and show all functionalities. IX0 here is just a single number basically. I don't know, I never used this really, but probably it's just nice for if you want to do some operations that you can also specify an IX0 array. Let's stick to 2-dimensional, and then you see now it actually compiles. We can run the test and it works. Maybe let's print it to see how it looks. So we can either debug it, right? And when we debug it, you see, okay, we have an array of 2 rows and 3 columns. There you see the shape, 2 rows, 3 columns, and there is the stride 3 and 1. Strides are just, internally it's just laid out like flat data, and the strides are just an instruction, so ndarray knows how to iterate over the stuff. So for example, when you just want to have row 2, where does row 2 actually begin? And it's just an instruction, so it says here, to get to the next row, you have to jump 3 numbers, right? So we have to jump to this number to get to the next row if they are laid out flat. And 1 means how can we come to the next column. Yeah, so we just go for the next column, we just jump 1. So that's basically this instruction set. And the layout here just means we have row first, that can be also represented as column first. So how it's laid out. Like we looked in this audio buffer stuff, if it's basically interleaved or sequential. Yeah, so that's the representation here. That works fine. So let's look into the other types we have here. This is the owned representation. If you click on this, you see, let's close this again. The owned representation just contains a pointer, a length, and a capacity. All good, so like a vector basically. But the other one we have here is the view representation. And the array view representation. And the view representation needs to be references to our type. So here we want to have references to F32. You see already that works. But we cannot just start with zeros now, because this function needs to create a new memory, and the view representation never allocates memory. It's just storing a pointer to a collection we already have. So we need some sort of data that is stored somewhere else. For example, here a vector of zeros, and here we want to have 6 of them for our shape 2, 3. So then we can use the function just from shape, exactly. So here from shape, then you specify our shape, so 2 and 3, and then we specify our data where it is stored. Then you see it's returning a result, and this is because this operation here could fail, because here you could have a shape that doesn't fit to those number of elements, right? So we need to unwrap here or return the error in our actual program. So let's check that this was working. Maybe this time we can print it out. Oops. And see that we actually have an array. So here you see display is implemented. The trait display is implemented on array. That's why we can print it like this. We can also use the debug representation with a column and question mark. Okay, what do we see here? The display operation really just displays our numbers. So we have 2 rows and 3 columns. That worked fine. Let's use the debug representation. And then you see we get some more info, like the shape, the strides, and the layout. Cool. And the last type you will need usually, it's also a view representation, but you just add a mute here. Yeah. Now you see that doesn't work because we need a mutable reference to our data. Let's make data mute and add a mutable reference here. And now this works, yeah. So the only thing, you only need this when you don't want to own the data, but still manipulate it. So now we can use this array object, we can move it somewhere else, change the data, and then this data will be actually changed, yeah. If we create an owned array with this data, then manipulate it, it would be a copy and not manipulating this data directly. So here we just have a mutable pointer to this vector. We can test this, for example here, let's make this mute. You can just index into it. So we have a 2-dimensional array, so we can use 2 indexes. The first one is 0 and the second one, let's maybe just use 0, 0, and then set this value to another value like 6. And now let's print our original data object, so this one. And you will see we actually changed this data, right? So this is just an abstraction over this data. And that's why I use this ND array sometimes for audio data, because this view representation is so nice to use, yeah, with this indexing. So, but I told you, you barely use those base types because they are quite complicated to construct, as you see. They are most used for generic functions, so you can really accept any type of array. But in our common program, we just use the type aliases, and they are on the highest level for the owned representation. They are called array. I see there's array 0 to 6 and array D. So for this type, we need array 2, and then we directly have zeros 2 and 3. And here the only generic we need to specify now is the actual type we want to have, right? So in this case, F32. So that's already a bit simpler to use than this, right? There's one thing in between. This is array, just array, and then we need to specify F32 and IX2 again. Yeah, so you can kind of select how much down to the space type you want to go. But this is the highest level one. Yeah? If you click on it, you see it's just a type alias for array IX2, and array is really just a type alias for ArrayBase. So what I just showed you. Then let's check out the view type. So this one. This is just called ArrayView2. And now we cannot use zeros again because we need some data that is already existing. So we can copy this function, so that works as well. And then there's also the ArrayViewMute. And we want 2-dimensional. Let's get a mutable reference again. So you see that works fine. Perfect. So those types are a little bit easier to use than the ones here, right? Also, the view type is kind of practical because any type of array that you have here can be converted into a view. So you can use our, let's call this array 1. We can take the array 1 and convert it into a view. You can take the array 2, which is already a view, but just create a new view out of it. You see it's kind of cheap to do. And also the array 3 and create from a mutable view a non-mutable view. Yeah. Then you will see from array 2 we cannot create a mutable view because it's not mutable inside of here, but from array 1 we can create a mutable view because it's owned. And owned data always can be mutated as long as you have a mute here. Yeah, I know it's not the easiest compared to Python, but in the end it really pays out because you know exactly which capabilities you have. Nothing can go wrong. Everything is lifetime checked. You know, nothing can be mutated in the wrong place. And when you work in Python with ndarrays, for example, it's a bit harder to know if the data now is actually owned or you just have a reference. And there can be sometimes issues with that. So that's really cool that this is so strictly typed. Just to create an array D, if you ever need this, the shape cannot be specified like this. Yeah. It needs to be wrapped in an IX-dyn. IX-dyn. And then you can specify it like this. And we still need the type, right? So here you have a dynamic shaped array now. That works as well. But as I said, stick to those whenever you can for performance reasons. But if you're just doing some tests, right, you can just create the dynamic array. Now, what I thought is a bit complicated in the beginning is when I want to receive arrays in a function and I want to manipulate them. How do I do that? So, for example, we have a function add array or arrays, and now we want to receive it here. I would recommend mostly just going with views in here because I showed you that everything can be converted into a view and it's very cheap to convert it into a view. So that's a really nice thing to use as an input for your function because you know it's cheap and yeah, you can. It doesn't matter from outside what the user actually had. If it was even this array cow and arc array, those are more complex types you don't need in the beginning. Let's just specify the array here. So array 1 is an let's take a mutable array view mut 2 f32, and array 2 is an non-mutable array. And here you see we don't use references. You can also use references, that would work, like we learned before, so that we don't move it inside of here. But the views we can actually move. That's no problem, because we can always create new views and move them somewhere else, because they are so cheap to generate. And that makes it a bit easier to handle, because we don't need those complicated references anymore. And still inside of that, it's still lifetime checked, so you cannot run into any issues, even though you're moving stuff inside of here. And now we can, like the not recommended way, but so you see how it looks underneath, would be to iterate over the rows, for example. For row in array 1 dot number of rows, we need to go from 0 to number of rows. And then the same for the columns. Obviously, we don't do any check now if array 2 has the same size, so that's a simplification. You could use the minimum between array 1 rows and array 2 rows to always be safe, or put an assertion at the top. And now we could just use array 1, and we index in it with row and col, and then just add the second array to it. This now doesn't work, because as we move it inside, we have to specify again that we are allowed to mutate this value. All right, that works. Let's test it maybe with our, maybe let's just use some new data. And this here. I don't know what we do here. Let's just do more. So then we need those two, an array view and an array view mute. Let's do it like this. And we want to have data 1 and data 2. And then call our function add arrays. Add arrays with array 1 and array 2. So this works because it's already a view. But you can also, if you have a different type, just call view here and view there. This has to be mute, sorry. And you see you have to add mute here as well. And this is basically how you call it. Yeah, you can use any array and always create a new view that's created here and then directly moved into the function. And that's usually no problem. Now let's check what we get out. It should be added to array 1 now. And it failed. Out of bounds indexing. What was the problem? 2, 3. Ah, yeah, this here failed. We don't have 6 values in here, right? So let's use 2, 2. That we have those 4 values. And now it worked. We have 5, 7, 5, 7, and 9, 11. So perfect. Our math function here worked. If you want to do it even faster, because this here has additional bound checking. Yeah, so when we index like this, it makes sure that those are still inside of the array. You can also use some unsafe functions just to speed up if you would be in a hot loop here. And this is array1.uget. And then you just use this index. And add array2.uget. So this works. You can also specify it like this, row call. And this has to be uget mute. And we need to dereference this because we get a reference here. Yeah, so you can also do it like this. That would be the unsafe one, but it is safe through here, at least for array 1. For array 2, you still need to do some checks, right? But it would be the same just to do, there are some functions to make that a bit easier. So for example, there is azip, and the azip macro just lets you combine as many arrays as you want. So you can say A, that which is the name of our value in array 1, and B in array 2, also by reference. We put this here in brackets, and then we just say here A plus equal B. This is just a very special syntax, but now you can even add more arrays here to get all of those by all of those single values. So that's one option, but it's not the nicest, also not very easy to write. I actually don't love this notation. The easiest would be just to say array 1 plus equal array 2, and we get array 2 by reference. And this works as well. Let's just test it. Here you see 5, 7, 9, 11, so that's no problem. And you can also use the underlying BLAS implementation directly. And this would be array1 dot scaled add. Then you see perform the operation self plus equal alpha times right hand side. That is done efficiently with the underlying xpi and BLAS if you activate the BLAS feature. So alpha would be 1 because we just want to use our array 2 like it is, and then take array 2 here. So that works as well. Let's test this. And we have 5, 7, 9, 11. Cool. So scaled add is also a possibility. You have loads of functions like this. Yeah, just check them out. There's cool stuff like you have iterators again. You have maps. Yeah, also map by value, map in place. Then you can just directly change the values inside. So there are a lot of nice functions. But yeah, this would be too much to go over all of them. Just read the documentation, and you mostly find some examples here how it works. Perfect. That would be it. Again, check out the documentation and feel free to ask any questions in the comments. I'm happy to answer them. Yeah, I think that's a good foundation. So I could show you some more in other videos, like how we can actually abstract audio buffers with it and which parts are real-time safe and which not. But yeah, I think this here, specifically this part, how to write a function that receives arrays, is very useful information. I needed a while to figure all of this out. But now I'm actually quite comfortable in using it, although in the beginning I was a bit annoyed by all those different types. Yeah, but especially in complex projects, it's really worth it. All right. Thank you for watching and listening, and see you next time. Bye bye.